Hello, sir. Hello, sir. രണ്ട് മൂന്ന് മിനിറ്റോടെ വെയിറ്റ് ചെയ്യാന്ന് വിചാരിച്ചാണ്. കാരണം ഗൂഗിളിന്റെ എറർ നിമിത്തമാണല്ലോ താമസം വന്നേ.
എല്ലാം റിസോൾവ് ആയി തോന്നുന്നു.
സോൾവ് ആയി തോന്നുന്നു. ആൾക്കാർക്ക് കേറാനൊരു ബുദ്ധിമുട്ട് വന്നെങ്കിൽ ഒന്ന് വെയിറ്റ് ചെയ്തേക്കാന്ന് വെച്ച് 2 മിനിറ്റ് വെയിറ്റ് ചെയ്യണം. Okay.
Satish.
Yes. Good evening, person. Yeah. Yeah.
Okay. Thank you for sending the
link.
Glad.
Yeah. Welcome. സാറ് പറഞ്ഞായിരുന്നല്ലോ മൊത്തം. സാറ് ഇന്ന് സാറിന് ഇൻഫോം ചെയ്തായിരുന്നല്ലോ ഏകാദശി അല്ലേ?
It is cold here. Cold.
Oh, okay. Cold, okay.
So unusual cold.
Oh.
Hello, Satish sir.
Okay. Shanoja.
Can you hear me, sir?
Hello?
Can you hear me?
Yeah.
Okay. Thank you. Hi, Kalyanan, sir. So happy to see you after a long time again.
I also have the same feeling. Last time also we had that feeling.
Yeah, I really wish to see everyone in person. Maybe like next time when I come there.
Please come. Yes.
Yeah. How are you doing, sir?
Going well at the age. Still going with whatever these youngsters are doing in the department. So I joined them this occasion to see you all. I don't miss it.
Yeah, sure. Are you somewhere closer to Trivandrum or you are somewhere in like Tamil Nadu? Chennai?
No, I am in a village very near Tanjore.
Okay.
Tanjore. So I am in my native village.
Oh, great. Yeah.
Periodically going to Chennai, and but now for the last about 6 months or 7 months, we are confined to the village without any work. I think I'm better.
Yeah. Is that the native village for you, or you just settled up there?
No, this is my native village.
Native village, okay.
I have some agriculture operations going on, so I have to.
Oh, nice.
Yes.
Yeah, nice. Yeah.
Hereditary property. Yes.
That's true.
Nice. Yes. Carry on. Sadiq?
Yes, sir.
You can start. She's waiting.
Yeah.
She's waiting.
Yeah. Okay, sir. Okay. Now there are 45, I think. Several are, I think, waiting probably. Even then, let us not waste our time. Valuable. Yeah. Today, the morning session handled by Professor Kosumovisky with regard to our international workshop on distribution theory and its applications. And now we have we are very proud to introduce Dr. Shanoja Naik. Is an alumni of our department, especially, and she did her PhD from even though at MG University, and thereafter PDF in University of Regina, I think so. And thereafter she's working in the Health Research Outcome Center, Toronto, Canada, presently, and working as a senior data scientist. And she is a very active researcher and did several, I think she's an expert in the area presently, or getting expertise in the areas of survival modeling, credit risk analysis, time series, etc. So I found that we can utilize her to explain how distribution theory and its in application way in these areas of, especially in the credit risk analysis and such a actuarial areas. In fact, Professor Kanchan Jain is an expert in the actuarial science. She's also joined with us. And we have a Kalyanan sir, or my professor, is also with us. And several faculties as well as researchers from several parts of the world are already here in this group. I think so. And also, Professor Violeta Piperigo from Greece is also joined with us, and several others, in fact. I utilize this occasion to once again extend our gratitude to Shanoja for accepting our invitation to present some of her works useful for our MSc students, especially, and research level students, how to mold them or motivate them to the areas of such areas which are related to the statistics. And on behalf of the Department of Statistics, University of Kerala, first of all, I welcome all of you to this session, especially Dr. Shanoja, for and applications, or in what way it is helpful to the, or it is our distribution theory and statistics works there. With great pleasure, I invite you, Dr. Shanoja, and I hand over the mic to Shanoja to continue her presentation, since we have some time, in fact, lapsed due to the technical issues of the Google platform. Let us start the program. Once again, inviting all of you, especially our professors, Professor Kalyanam sir, Professor Kanchan Jain, Professor Piperigo, and other professors. And Professor Shanoja, please start your presentation. And I warm welcome to this group. We are all waiting for your presentation.
Thank you very much for the wonderful introduction. And so there's sir, I think I can share my screen now. Am I correct? Can you see the screen now?
It is coming, yeah, now it is okay. I think this can maximize if possible. Yeah, So, fine.
Yeah, but I cannot see which slide I'm presenting on the view.
Yeah, now this is, first slide, that is your heading title slide.
Okay.
The Vishad stochastic formation. Yeah.
Okay, so thank you very much for the wonderful introduction, Professor Sadish, sir. And at this moment, I'm so honored to be back in my department. I would like to call it as my department, which I graduated almost 18 years before. Typically, I would like to say this is really a great moment in my life where I'm back in my department for presenting one of the research topic in front of my professors and a great process around the world. Thank you very much for having me today. The topic for today's talk is the Vishad stochastic correlation model and application in default risk modeling. Before I get in the topic, I wanted to introduce myself. I'm working in Health Research Outcome Center, Toronto, also the adjunct faculty at Laurentian University, Department of Mathematics and Computer Science. I'm working in the research lab where my concentration is mainly on health research. However, I'm working on other research topics based on the collaboration with various faculties within Canada. So this work is typically a challenge I received from one of my colleagues at University of Regina during my postdoctoral fellowship, where the challenge was to model data, the description of the data. I'll explain the context later time. Now, the Vishad stochastic correlation model and application in default risk modeling, it's very clear that it's a multivariate concept. However, the entire topic is really rich in terms of mathematical expressions, derivations, so lots of content. So when Sadish sir asked me to deliver a talk, initially I was thinking it's just for 1 hour, then later decided to go another half an hour or 45 minutes, but now we already lost like 10-15 minutes due to technical issues. Now, about the Vishad stochastic correlation model and default risk modeling, it's a combination of actuarial science and application of distribution theory. Then I'll be going through some of the basic concepts. I'll start off with some basic concepts and going deeper to the actual problem and how we ended up with the stochastic correlation model for sovereign credit risk. As you see, this is the outline of the talk, but I need to cover lots of area in order to get in how we ended up with the Vishad model for the sovereign credit risk. So I'll go through some of the concepts like a probability theory, stochastic process, stochastic calculus, then some contents related to ordinary and partial differential equations. Then I will explain what is sovereign risk modeling and what are the available sources and limitations of the data. Then after that, it's how we developed the model and how we calibrated the model and the model structure that we developed specifically for sovereign credit risk. So the derivation is a little bit difficult to explain through a presentation slide. However, I'll try my level best to show how we derive the expression, what are the challenges in getting in the derivation, what are the problems in optimization during the calibration of the model. Now, in order to proceed the actual model specification, we started off with the Kalman filter algorithm, and the code was developed. The calibration was successful. There are some pros and cons and barriers within the constraints that we developed. So the project is still undergoing. So the research article, one of them is published, the other one is still as a working paper between me and my colleague. So I wanted to start off with the probability space. These are just like a basic idea of the probability space, what is a sigma algebra, and how we define the probability space with respect to the measures and measurable space. I'm not going in that detail for the probability space. The reason why I integrated the slide here is that I wanted to tell you a small story during my master's program in the department. So I don't know, Yagin Thomas sir is in the audience list. He was the one who taught us measure and integration. And the first assigned presentation was like giving a typical topic for each student, so they can give like one presentation, just like a 5 to 10 minutes presentation for all students. So when I got my turn, I was so nervous and couldn't even go through even like 1 or 2 sentences. So I just left home and didn't come back for 2 weeks. So Yagin Thomas sir called me, and my mom contacted him because I was at home. She didn't know what happened. So Yagin Thomas sir called me and said to come back. So that was an advice, almost like went 1 hour, which motivated me highly to complete my master's program. And that is how I'm here. So all credit goes to the department throughout my life journey. So whenever I start with the probability space omega script p, then I always remember the department in my process. And now a probability measure theta is defined on the measurable space omega f. We know that for the null set, the probability measure defined for 0 and for 1 when it's defined for omega. And we also know that it's disjoint under the closure. We need to define a filtered probability space in the sense F is defined in the family in which there is a subset is defined for all values within this 0 less than or equal to s less than t. Then the sigma measure contains F, the null set, which is the complete filtered probability space. So the entire progress from here onwards is defined with respect to the filtered probability space, omega f theta, and the filtered measure, capital F. In financial engineering, we use a lots of theoretical programs, and we use the stochastic processes to model the financial instruments such as like the stock price. We sometimes model the volatility of the stock price and interest rate and foreign exchange rates. These are not the fulsome list, but we can just think about like different types of modeling and different various structures that we used in modeling these type of financial instruments. I'll explain a few models during the talk, specifically the CAR process in some of the other models based on the particular model that we used for this particular sovereign credit risk. Now, coming to the explanation, a stochastic process can be defined on a sigma algebra space. For any stochastic process, we can define the neutral filtration fx as defined as ft for a specific value of t, specific time value of t, in such a way that t can be in between 0 to t, and xs is defined, and corresponding the inverse function is also defined. Now, for any measurables random variable x defined on any subfield G, then we know that the conditional expectation of x satisfies certain condition in such a way that for the given information G, then expected value of x is equal to expected value of y z when y is defined for expected value of x given the information G defined on the f measurable random variable. Now, the Brownian motion is the best example for a stochastic process in which the most valuable information we can collect in a simple derivative way. So the Brownian motion, which is just like, again, the basic assumption, but we need these assumptions and the concretized examples to go forward in explaining the sovereign credit risk. Now, as we define the Brownian motion, the important part I wanted to specify is that the independence of the difference between the two successive time values. Now, for given specific example, we can say that the Brownian motion is a martingale. Now, the proofs are available, and I think like during our course of master's degree and other programs, we always come up with these are basic examples of the stochastic processes. Coming to the stochastic calculus area, we always deal with the probabilistic definition that comes under the calculus within the Ito calculus notation, which has wide application in financial engineering. When I say Ito calculus, that comes under Ito integral and Ito processes. Those two are really huge area where we need to integrate and understand the concepts well in order to get in the financial engineering area. Now, I'll give a few steps that we actually needed in order to model the sovereign credit risk. So one of the part is like Ito integral process. Ito integral process is defined underneath, where the integral process itself, it can be decomposed is in terms of limited values of the sum of the finite sums. Sorry, limited values of the finite sums. Now, this is the basic idea for all the stochastic processes that we used in financial engineering. When a stochastic process xt is defined in the form xt, which is x naught plus as integral 0 to t mu s ds plus integral 0 to t sigma s dws, where sigma t and mu t are functions of t, then we can also express the integral formula in terms of the differential notation. dxt can be defined as mu t dt plus sigma t dwt. And as I said before, sigma t can be decomposed in finite sums. So one of the most commonly used Ito process amongst the whole list is the geometric Brownian motion, where geometric Brownian motion is like a highly used for most of the simple models that we used in financial engineering. As I said in my previous slide, geometric Brownian motion follows a stochastic differential equation in the form dxt equal to mu dt plus sigma dwt, where mu and sigma are specifically constants. The general equation comprised of mu t and sigma t. Mu t and sigma t are functions of t. Usually they are comprised like derived from the mean and variance of the, can be explained in terms of mean and variance of the model. Now, for the geometric Brownian motion, xt can be expressed in terms of exponential function, where the exponential function comes with the constant mu minus sigma squared t plus a linear combination of dwt. Now, Black and Schultz 1973 modeled the dynamic of the stock using the geometric Brownian motion, which was the starting point of how we defined the application of GBM in different modeling purposes. Now, Ito's lemma, I wanted to explain the Ito's lemma here, instead going in deeper when I explain the sovereign credit risk, because Ito lemma is the basic introduction part of like Ito's calculus. As I said before, there are two parts, Ito's integral and Ito's process. So Ito's lemma help us to define how the infinitesimal operator can expand and how we can derive the differential equation and get a solution in comprised form, which we can use for the model, which we can use as the solution for the model. So here you can see underneath an expression gxtt, where gxtt can be expressed in terms of the initial value plus the integral with respect to differential of the function g. The differential can be considered with respect to the time variable t. And the third part of that equation is differential with respect to x and integrate it out. And the last part is the half times integral 0 to t, which is the second derivative with respect to the variable x. So now moving on, we need to generate some kind of integral equation which relates to the integral that can be comprised with respect to the time variable t and integrate with respect to the space variable s. So in moving forward, we will be considering a state space model, where the state space model, which means the state space s can be considered and time variable t can be considered, and we need to integrate with respect to x, the first derivative and second derivative, and use these equations, to get a solution for the model that we actually define. Now, the best part of the geometric Brownian motion is that we have a closed form expression, as I showed previously. The closed form expression in the sense xt can be expressed in terms of exponential function. Now, that is not the case for all the other models all the other processes that we define in the literature, because a CAR is one of the main focus of this talk, that we use the dxt. Just remind like what we define. It's mu t dt plus a sigma t dwt, where mu t can be alpha times theta minus xt, and sigma t can be sigma times square root of xt. Now, in this model, we can have xt, where xt is defined in terms of like a variance notation. I will explain that in our model too. So this one means like a xt, and the only condition is that xt and wt should be independent to each other. Now, again, assume that alpha, theta, and sigma are constant, which are independent of the function t, and these values are application in interest. Sorry, these processes having applications in interest rate modeling, stochastic volatility modeling. There are pros and cons for the CIR model. The main part is that there is no closed form for the representation of the CIR process, and however, we can say that we have existence of the solution for the stochastic differential equation that we defined on the top, dxt equal to alpha theta minus xt dt plus sigma square root of xt dwt. Now, because of the same reason, there is no closed form expression for CIR process, but existence of the solution as for the stochastic differential equation guarantees. Because of the same reason, what we actually do is that we assume a solution for the given processes and move forward and derive. It's kind of like we can explain it as a reverse engineering. We start from the solution and come back and check whether it satisfies all the constraints and parameters in assumptions. Then we can conclude that the defined solution can be considered as the existing solution for the model. So in another way, we can say that the solution that we define is based on the data that comes in hand. So the solution could vary. It's not a unique solution that everybody can define based on the actual data problem. As we know, the data is unique everywhere. None of the model worked for one structured data is not specific to other structure. Maybe we can think about just like modifying or making assumptions like variations in assumption, then use one model to the other model for individual data set. Now, underneath, there is another example, which is called Austin-Ulbach process, which define dxt. Dxt is defined as minus alpha xt dt plus sigma dwt. So these are just like basic assumptions, or everybody can go through some of the literatures available and you can get more information, or there is a book which is typically available we can also consider. There is one publication, it's a book, Oscar 2003. So you can see all this information about the ITO process and CAR processes. CAR processes in that book. As I described before, for the CAR process, there is no closed form expression. So what we can do is there are two-way processes. Either we can assume a Laplace transform in terms of a defined solution. Defined solution in the sense the solution is not actually in a completed form, but it could be a function of the state variable or a function of time variable or a combination of both. So for the CAI process, the Laplace transform is defined in terms of an exponential function. So the exponential function is generally defined as ASU AT, where AT is defined as the processes, and a linear combination of BSU. So ASU AT plus BSU, since the Laplace transform is in the exponential form, then we also call the CAI process as exponential affine processes. Now, in our model too, we use kind of like a similar assumption and came up with a differential equation solution, and that is how we did the reverse engineering for the data in order to calibrate the model. Now, in CAR model, the ASU and BSU are defined in a certain way such that the partial differential equation with respect to S, partial differential equation of A with respect to S is defined in terms of a sigma square T and function of A and A square. Now, BSU, the partial differential equation of BSU, is also defined in terms of K, the constant K, theta, and ASU. Now, these equations are called the Riccati equation, which is very famous, where we can obtain the solution in terms of the constants K, S, and Weber U. Now, as I said before, these expressions are defined in terms of exponential functions, so we can consider CAR process as an exponential affine processes. There are two more theorems I need to bring your attention on, because Grisenow theorem, the first version and second version, are really important to understand the actual concept of how we can find the solution for these kinds of processes. Now, the theorem itself generally saying that we can have the process A and we have integral equations, then we consider a vector space in such a way that its expectation is finite, then we can have a probability measure P, which is equivalent to the last equation beta t bar, where beta t bar defined on beta t plus the integral with respect to theta s, where theta s is defined, which satisfies certain conditions. It's a lengthy proof we can available. So for the proof, you can also check also 2003, which is on page number 163 to 164. The assumption is basically important, because when you consider exponential of an integral that should be finite, then we can identify corresponding E2 processes. So I'm skipping that one due to the time. Coming back to the derivative pricing, one of the most important results of the modern financial engineering is to give some formulas for the price of the contract with underlying payoffs in nature. The contracts can be in contingent claims if the underlying process is defined as like a vector of asset which guarantees information ft up to the time t, then the contingent claim at maturity t is any ft measurable random variable. When I just say asset in like a information related to the asset, the contract, like a given technical terms that are coming up in the next slide, you can compare that with an individual product that you're getting from a life insurance company or from banking sector you usually receive. When you say the asset for a single family household, the asset could be just like the income that we are receiving from the 2% or 3% from the home. However, there are other sources you can contribute in, maybe like a small business or maybe like a large business. That is for the single household. But when you consider a bigger, larger firm, something like a bank, then the asset could be contributed from many sources. At the same time, you can consider the debt as well. So there are two parts. The money is coming in at the same time. You need some the money from other resources as well. It's kind of like a logical statement that we always consider for the business firms. So in most of the simple cases, when we consider the asset, that asset could be a contribution from different factors. That is how I written, like the asset S can be in vector notation a combination of a few things together. Now, these are the technical terms that we usually use in engineering. The forward contract is an agreement to buy or sell an underlying asset at a specific maturity date for a specific price. Let's think about the mutual funding that insurance companies usually give it to all people around the world. Now, when you go for to get a mutual fund, then usually they offer lots of things. They could be offering you a finite maturity amount that you could get towards the end of the time frame. Or they could be saying, okay, you deposit your money here, then we can give just like a, I don't exactly remember what's the interest rate now, maybe like a 10% interest for accumulated interest for you in 5-year or 10-year time frame. Or another way is that when you put money month to month, contribute in your mutual funding, that actual mutual fund will go in other resources where your money could be like varying with respect to the stock market. So suppose you are investing this money into GMC. I cannot compare what comes in India, what are the typical mutual fund agencies. Here is the General Motors company. Those are the highly huge stock market holding price companies. When you give the GMC, you contribute to the your product. That contribution will go and rotate with the stock price along with the GMC company. Then what the GMC company is doing is that with respect to the stock market increase, each contribution, that contribution may not be that huge in our individual mutual funding. However, in the long run, when you consider 15 years or 10 years time frame, that contribution will be huge. Instead, you just calculate your mutual funding within a single product. I'm not a promoter for the mutual funding. This is just an example. So the idea is that when you contribute to a larger firm, even the 1% contribution back is really like matters. That means it accumulates to the mutual funding. So it could be more than we actually get in a single time frame. So just remember, when you go for mutual funding, it's a two-way contract. You could be agreement. You could be going within your insurance provider along with the other company. So there are two ways you need to consider. So ST and F0 T are to be considered, where F0 T be the forward price seen at the beginning of the contract, and ST could be the actual price you will be getting towards the end. Then the risk neutral variation, the term specified, because there is always a risk compromise with what you are depositing in a bigger company. Let's say you contribute to your insurance provider and they contribute to GMC, and successively in 2 to 5 years, maybe because like a recession effect, the GMC stock price go down, or any of the factors that affect to a particular company. So those 5 years, you may not be getting enough contribution from the company back to your individual contribution. However, you can get just like a better overview. But according to the agreement, it could be fixed in the sense, let's say the agreement could be saying you will be getting 1% back at any time of your time frame, but on the top you will be getting from other companies. But the contribution from other companies will not terminate the overall contribution for the individual product. So forward rate agreement is like a two-party agreement that certain interest rate that can be applied to specific principal in the sense amount you contribute for the future time period. Now, futures contract in the sense an agreement to purchase or sell a given asset at a future date at a preset time. So when you say that, okay, I'm going to keep this mutual funding for 5-year time, then according to the agreement, there would be some contribution saying, okay, if you terminate this contract within 1 year or within 2 years, you would be getting penalized. So those kinds of agreement will help both parties. So that gives a kind of like a termination. Maybe the insurance provider will say, if you terminate the whole program entirely or terminate your funding and you withdraw the funding from your individual product, then you may not be getting just like a 5% or 8%. Again, I don't remember what comes under the insurance rate and mutual funding rate in India now. The main difference between the future contract and forward contract is that for the future contract, the profit and loss are settled on a daily cash flow basis, which I explained already. Therefore, the credit risk is not that significant. But the payoff, as I said before, when you have not signed that contract, then what happened is that whatever be the termination that you're getting from your insurance provider, you need to compromise with those stakeholders. So because of that, your expected value will terminate. So whatever your expectation will go according to the contract base. It depends on how long you are keeping your product. It depends on how short you terminate your product. Now, coming to the swap, it's a financial instrument which are used to exchange cash flows at fixed points in the future. Now, to enter into a swap, no cash is needed actually. So one type of swap is the commodity swap, in which exchange of a fixed cash flow with a floating like cash flow occurs, which means that like I'm starting a private banking, then what will be coming into my contribution as a bank, then what I wanted to know is that how can I grow this money that I'm getting in my private banking sector. So I always think like what are the other sources I can contribute in. It may not be like a single provider which gives you like a stock market rate, but you can think about other resources where the floating cash flow depends on the price of a certain commodity. Now, these are technical terms we actually need in financial market. Also, we do have option, which is also important. And option is a contract to sell or buy a tradable asset prior to at a specific maturity date. Now, let's say you're getting a mortgage from a bank in order to build your home, and after 2 years, after 3 years, you cannot even contribute a single money back to the bank. Then what you do? You might have to go through different criteria. So those kinds of this is just an example. These options and these kinds of terms are really matters for banking sectors. Actual banks, they deal a lot. So there are different types of options available. European option, American option, and these are well defined based on different values like a specific strike price and an asset price. So I'm not going in details like Asian option, barrier option, look back option, then compound option. So there are 12 or 16 kinds of options we can available from the banking sector. So actually, Basel Committee is the regular provider for the entire world. They contribute to how to dominate or how to stick on with the market price in different levels. So European Union usually goes with the Basel Committee. And the recent one was there was huge changes in their policy. Sorry. For any tradable asset with the dynamics, DXT, where DXT is defined, a little bit elaborated, mu XTT dt plus sigma XTT dBd. The martingale measure theta is the measure generated by the Grisano's theorem, which I already briefly introduced, like what the Grisano's theorem is that. Now, this notation dxt is derived from the equation xt equal to x naught plus the integral formula. Now, this dxt can be defined in terms of RT, where RT is the risk-free interest rate. Now, this is the starting point of where we came up with the model for our data. Now, we are assuming that the price process for the underlying asset is modeled by the geometric Brownian motion. The market is complete and X is given as the contingent claim, and B not be a risk-free asset for a price process. Then we can define dB not T as B not T RT dt. Then when you integrate out, it's just like a simple equation. You can easily identify B naught T in terms of an integral notation for RT, where that integral expected value of X integral is defined as a VXT. Now, also we use the risk neutral variation formula using the prior information which are available. So the notation is that a VXT can be expressed in terms of a constant for the e power. The previous equation is e power minus t integral t to t r of u du. Let's think like r of u is a constant. When r of u is a constant, that exponential can be treated as exponential of minus integral a constant du. So that could give us e power minus r t minus t and the expected value of theta with respect to x for the given ft. Now, Black-Scholes partial differential equation is also considered, where that equation gives gt plus rs gs in the sense differential with respect to s plus half a sigma square s square and second derivative with respect to s minus rgst. Now remember, r is a constant here, and we consider mu t and sigma t are constants, so sigma t is also a constant. Now we need Feynman-Karg formula, where Feynman-Karg formula describe how we can expand this to an infinitesimal operator. So there is always a relation between the Feynman-Karg formula and the stochastic formula that we already defined. So based on those one, we can actually define the entire function of fxt. There are certain conditions. The second and first derivative with respect to x and t can be defined within the equation. That equation is defined in terms of the trace. So this is the basic where fxt can be individually expressed in terms of the expected value and integral notation. When you see the equation seems to be really huge and big, but when you come up with the actual derivation, I will give just like a few steps. You can find the function fxt. Now I'm pausing here just to give you a few minutes. Among the key areas covered previously, the probability theory, stochastic process, stochastic calculus, ordinary and partial differential equations, which of the contents are familiar to you? All of the contents, some of them, and none of them. You can put your answer in the chat box, please. I'm expecting at least a few. Sorry, I didn't see the chat box here. Okay, so I'm moving to the actual data description and explanation, how we came up with the sovereign credit risk model. Now, the problem with the sovereign credit risk model is that, like, the asset is actually not visible. Let's say in India, generally, can you identify at least a few assets that coming in for the entire country? Then if the asset is not, the asset information, when I say asset in the sense, the information regarding to your asset, your contribution is not actually visible or not actually defined, then how can you model the asset in general? Let's say you have you're considering YT as a variable, and you wanted to model the data based on all the assets that a particular bank is holding. Then you can say, hey, here is my asset, and these are some of the contributions. Based on the contribution, based on the swap, and based on credit worthiness index, then this is your model. These are the credit risk model that I'm going to build. This may be like a linear association, maybe a non-linear association. You can build and identify corresponding model based on the entire asset. But in a country asset, how can we find, just like we don't have any kind of assumption, we cannot even just say the asset from the individual separate products are not just like contributed in the same way, then there may not be like a standardized procedure to go forward. So the first question asked by my friend is that like, hey Shano, can you model this? This is a challenge I'm going to give it to you. What do you think? So I think like it was a big learning curve for me in order to understand on the actuarial concept, along with some of the ideas that I learned in my master's program. So the first thing came in my mind is that like maybe we can consider YT as just like a stochastic variable comprised of just like say YT, maybe depends on YT minus 1. That was my basic idea, because my experience was I was working on time series modeling. So YT can some kind like depends on like previous observations, and we can consider like non-Gaussian error variable, then just model it. But there were like lots of barriers in that one, because my YT is like unobservable. What I'm supposed to do with that one? Instead, I can have like a swap and other indices that I can get the data on. So the data is again based on two time frames. Some of may remember that 2008 and 2009 there were a huge recession. During the huge recession, we know that like there were lots of variations in stock market. Most of the stock market went down, maybe due to COVID, and after this we may be coming back to the same scenario later time, who knows. So, and a portion of the ongoing European debt crisis. So due to the recession, most of the European unions, they highly affected. So the data is coming from European sovereign, which comprises two groups. Those data that are among the most distressed one, so those are coming from Group D European Union countries, and the most affected ones that are coming from Group A companies. So it's not only just the recession is affected. So the recession is affected in many ways throughout the company's sovereign asset. Also, we need to categorize the country's asset in different countries in different levels, Group A to Group D, where Group A is the most affected ones with the less affected ones. Now, two criteria were used in the selection process for the sovereign. The first one is availability of an adequate amount of data. Some of the data are really missing, so we cannot do anything. Now, the 12 selected sovereigns have the most complete data after July 2008, and all of them have more than 680 daily observations on the swap spread from July 2008 to May 2011. Actually, I'm not supposed to show any of these things because it's a data privacy concern, but this is just like a snapshot of the actual data. So you can see that the names of the countries are given and corresponding year-wise indices, and there are lots of missings in the swaps for certain countries. Now the question is like, how can we, there is no value corresponds to the actual asset of the country, then how can you model us? In the corporate setting, if the asset value of the firm are not directly observable, as is usually the case, then what we usually do, we usually consider the log return on the market value of equity, and it's taken as a reasonable proxy for the asset log return and is used as a credit worthiness index. Now, for the sovereign credit risk, the returns on the market value of a sovereign asset are also not observable. As I said before, it's not that clear how much you are getting in. It's easy when we just consider one or two, let's say in our home, like how much is the earning from your parents, then what is your earning? So altogether, what's the total income for the family? If you have a business add on, then we can find the asset. But on the other hand, for a country, it's the sources are not available, the money incoming and outgoing are not accountable. Then how can you model the data? In the literature, either the yield spread of sovereign bonds are often used to analyze the credit risk premium of the sovereign debts. Now, the second criteria is that the second criteria is that the research should make sense intuitively. As I said before, like for most of these type of models, we assume that the solution exists for the processes, and we come back and do the reverse engineering to get and say this solution satisfies the differential equation and this is the model. But even in this case, like we can either go back and assume solution and start off from there and check whether the differential equation can be obtained from the existing model that we define. So the two ways, we consider both ways and check like which one is feasible. So I'll explain like how we develop the model based on the data I shown you previously. I'm skipping the previous slide. The last challenge is that unlike corporate credit risk, it's not straightforward to define and measure the creditworthiness of a sovereign country, partly explicitly due to the lack of reliable asset data. So other data are not available too. So I'm getting kind of echo. Thank you, sir. So this is how we started off with the model building. So based on the data, as I said before, here onwards, it's the actual derivation was just like a M variable derivation, like a matrix is defined, everything is defined for different countries. So 1 to M is defined for the presentation. I just bring it down to bivariate case. So here we consider two countries. It's just like two European Union countries. We wanted to compare them. So two countries were considered where the assets are noted as A1T, A2T. Then the log return, it's very clear when we define the asset, the log return is YT, which is ln of A1T and A2T. Now, let's define the RT. RT is the risk-free interest rate, and Q denote the probability measure defined on the probability space, and where the risk-neutral measure RT, here we are not going to consider RT as just like a constant. Instead, RT keeping as like a function of T itself. Now, one I'm supposed to put it bold. I don't know why it's not appearing. One is a 2x1 vector, and WT is a Brownian motion. Now, we consider that YT and WT are independent as well. Now, coming to the variance processes, as I described before, we need to describe the XT. XT is a part of the volatility process or the variance process, which belongs to the set of 2 by 2 matrix. Since it's the variance, we know that it has to be like positive definite matrix. So XT can be defined in terms of XT and ZT, where XT and ZT, where ZT is again a Brownian motion. So the initial statement is that YT itself is considered as in terms of RT and WT, where WT is a Brownian motion, and XT is the variance process, because here we consider square root of the variance process. So square root of the variance process in terms of like XT can be defined in terms of another variable ZT. And again, we assume that WT and ZT are also independent. So at this stage, I wanted to specify that the current work we are undertaking is by considering a dependent structure between XT and YT. In the previous equation, XT and YT in the sense the variance process in corresponding the Z result. Now, in the variance process, we defined constant matrices, where constant matrices are omega, m, q. Omega I previously defined for in the introduction as like a sigma measure, but here is just like a constant matrix defined for the variance process. Don't be confused with the two. And as I defined before, XT is a positive semi-definite and M is negative semi-definite. Because omega prime, we know like how can we build the construction that is defined in terms of Gindikins coefficients beta, where omega prime is a beta Q prime Q, where Q is also defined in two-dimensional metric space. Again, as I said before, T is a matrix of standard Brownian motion. Again, WT is a vector of Brownian motion. However, ZT is a matrix of Brownian motion, which is uncorrelated with WT. Now, under those assumptions, here I just put just like some matrices together, how we can see omega prime, what I mean by XT, the variance processes, and what is M and what is Z. So as I said before, omega prime, we can expand in terms of beta Q prime here. And also we have the variance covariance matrix, or I can say let square root of XT is defined in symbol notation as a matrix notation in terms of sigma 1, sigma 1, 2, sigma 1, 2, and sigma 2, 2. Then we know that the diagonal and off-diagonal elements of the whole matrix is like a positive semi-definite. So based on that one, what we can do, we can just say, we can identify XT. XT is again just like the matrix that on the right can be multiplied times X prime. So M is defined as just like a constant matrix, M11, M12, M21, M22. And ZT is also defined, Z11, Z12, Z21, and Z22. Again, when we expand the whole matrix and come up with a vector solution, as I said before, I just defined the 2 by 2 assets, Y1T and Y2T. So Y1T and Y2T are just like a linear expression in terms of variances and covariances, along with the risk neutral measure RT. Now, here we also assume that RT as the continuously compounded risk-free rate. Now, as I described before, this expression I already explained. DT is the depth per share. We need to consider that because of the risk neutral factor can be expanded, identified with respect to the depth. I will explain a little bit more context for that expression. Let's say you do have just like $50 in your, you do have 5,000 rupees in your hand and you owe almost like 10,000 rupees for someone. So when you owe more, then you are getting in a debt. But if you have like a more asset in your hand, more rupees in your hand, then you compromise that part. So always debt need to be considered because that is a risk factor you come up with your data values. So when you consider the risk factor, that could be in terms of the risk neutral measure along with the debt per each share for a bigger firm like a bank or other sectors. now we need to define the default of values. Default value in the sense, if your asset and I wanted to check the time, how long we do have presentation.
Hello?
Sir, what's the time now?
Now it is 7:15. 7:15.
So another 30 minutes?
Yeah. That's not
Okay,
clear, yeah.
thank you. Yeah. Okay, coming back to the default time, maybe I'll pause slightly here before I go deeper in the modeling terms and construction of the model. Do you have any questions for the basic assumptions that we expanded, or do you have any idea like how we can identify or how we can get in a solution for this model? Any questions? Okay, since there's no question, I'm moving to the next part. So, as I said before, you have a default, we need to define a default time. When we get default, when default in the sense, AT is your asset and DT is your debt. As I said before, your asset is lower than your debt, then you get default. I'll explain more. As I said in the previous example, you have like a 5,000 rupees in your hand and you owe 1,000 rupees to someone. That means the amount in your hand is lower than what you actually owe, then you get default. On the other hand, if you have like more asset in your hand, then you have like your debt is lower, you know that you can pay it off. So it's the same idea. We need to define the default time. The default time comes when your asset is lower than the actual debt you have. So according to that one, I can define a function SIT, where SIT is defined in sense AIT minus DIT is defined when your default time is larger than T. Let's say I'm saying you can take like 5 years to pay off your money. You can pay off in 10 years to pay off your money. But with the time frame, we need to pay off. If not, you need to get it down in the sense you are in bankruptcy. So there are two time frames in the sense the default time frame with respect to that time period, you get whether you get your time to pay off or you get in bankruptcy. Bankruptcy in the sense the bank will come and take out everything from you. So those are the two times we need to define. So SIT is well defined, where the default eta I can be reframed in terms of the SIT function, where default time is defined when SIT is less than 0. Now coming back to the log return, as I said before, the YIT is formed as a vector. It's actually an n-dimensional vector, but here I just described like a two-dimensional one. So the two-dimensional vector is reformed in terms of SIT. Again, the SITs are defined in terms of like AIT minus DIT. AIT minus DIT in the sense you always calculate what you actually owe and where are you in terms of your financial settlement. AIT is the asset and DIT is your debt. So rewriting everything in terms of your SIT function, we have like DS1T and DS2T are the vectors for the two countries. For those two vectors, we are going to define furthermore. Then going forward, I'm going to use this log return, the vector defined in equation 3, which will be the basic assumption. Once I get the solution, I can find a corresponding the asset for each countries. Now, we are also assuming that there's a survival probability assigned for each of those SIT, where survival probability is defined in terms of the measure Q. Now, this is the reason I explained the Feynman-Karp formula. When compared to the Feynman-Karp formula for P, the basic differential equation that we can obtain is that P can be expressed in terms of the first derivative with respect to the time and the infinitesimal operator. When I say infinitesimal operator, it's just an expression which we find the partial differential operator with respect to the state space and the time space, or S and X that we consider. So ASX defined in terms of AS, partial derivative of S, partial derivative of X, and a partial derivative of S and X, then the partial differential equation, the Feynman-Karp formula, using that one, the partial differential equation can be written in terms of PT plus ASP plus AXP, which is given in terms of 4 because there is no combination of S and X together. From the dynamics of ST, I'm not going in detail, but when you expand the ASIP from the dynamics itself, we can see that the second term, the term comes under the whole expression, entire expression, PT plus ASXP, that could gives you a simple expression for ASIP, where ASIP again is an infinitesimal operation or operator defined on the probability measure P, where that can be simply expressed in terms of the risk neutral measure and SI and DI, along with the variance covariance values from the variance covariance matrix XT. Now, in 1991, Brew defined a function where DST can be expressed in terms of square root of ST dBT plus dB dash T square root of ST plus n ln of dt, where BT is a Brownian motion. So this was the basic idea. We put it back in the equation because we need to express AXP, somehow need to just like get a concretized form, just like a simple expression, in order to identify the whole expression for whole differential equation to solve it. So AXP is based on this Bruce. There is one theorem that states on that publication in 1991, where if we have like a ST that can be expressed in terms of square root of ST and square root of ST dash, then that could be expressible in terms of the trace of a certain matrices that we consider. So based on that idea, based on the partial differential operator D, what we can do, the partial differential operator D is defined in terms of D over dou x11, dou over dou x12, dou over dou x12, and dou over x22, because we know that X is a matrix, that X is a variance matrix, a volatility matrix. Now, based on that one, the entire equation, the PT plus this is the basic equation, PT plus ASXP, P, by incorporating all these functional values in the equation, we can get 5. So PT, as I said, ASX can be expressed in terms of RT and SI plus DI. And finally, it could be a bigger trace matrix. Now, we need to assume the initial condition, because when you calibrate the model, your model always starts from an initial value. The integral expression exists in the survival probability expression. I will explain that in the later slide. Based on that one, we need to assume like where you starting off. Are you starting off with a simple value like a trial value, or you wanted to specify with a certain value which we can assume for the model? Now, in this stage, the expression in 5 is not that easily transformable. So what we have done is we consider yi as logarithm of Si plus di over di. Now again, as I said before, here we consider Si, where Si is the log return of the asset value. When we transform the variable, the whole expression in 5, the PT can be expressed in terms of WT. The expression is just like a narrowed down in simple form, because the RT, SI dp over dsi compromise with a few values that comes under the differential operator with respect to the probability measure. Here dx means the differential operator on the probability measure p. So based on that transformation, we again came up with a small equation. It's again like a multivariate. So it's in equation 6. Now again, we consider the transformation. Just wanted to emphasize one more thing. As I said before, CAR process is the basic starting point for our modeling. Then based on that, when we know that the solution could be an exponential form, because CAR itself is an exponential affine process. So we are somehow directing towards that. That's the reason we consider W again transformed to the exponential yi over 2. If I wanted to say here, yi is considered ln of si plus di over di. So we need to reframe coming back to the exponential function in terms of yi. Now coming back to that form, we can express ut in as simple as wi. The interesting part is that we need some initial condition turn on the function u such a way that u to 0x is 0 and u0 yi is e power minus yi over 2, which is visible from the definition given on equation number 7. Here's the funniest part. Now we stuck here. We don't know what to do. We come up with a partial differential equation. We come up with certain things. Then we know that this is a partial differential equation. What we can do next? So here, as I said before, it's part of reverse engineering. We postulate a solution for the partial differential equation. We are considering that u can be expressed in terms of the Fourier transform, where inside the Fourier transform, we again consider a function. That function could be either complex or real. We'll consider it as real once it comes to the survival probability. But at this stage, it's just like a mere partial differential equation we are going to solve. So the assumption is that u hat is considered as like a Fourier transform. We need to identify two functions. Again, CAR process, I wanted to remind you, the process itself is defined as e power minus a function of x comma s plus b function of x comma s. So it's the same idea here. We are defining two functions, two matrices, we are defining two functions in terms of tau and delta that could be identified in later stages. How can you find C1 and C2 in simple expressions of tau and delta, the time and the delta? Now, according to this Fourier transform, we can again, the best way is differentiate it once, differentiate it twice, and substitute back in the partial differential equation in order to solve the entire equation. That is the procedure we have done here. So I'm missing the first differential operator on the integral here. On differentiating once, it's an exponential, so you get just like the same term under the integral operator. You differentiate it twice, then you can get just like a differential equation in terms of a partial order second derivative and the function itself. Now, again, the operation in infinitesimal operator AX on the same function with respect to U transform, Fourier transform can be replaced, and we get the differential equation as intent. So now I put the equations underneath there because I wanted you to see the complicated partial differential equation came up with a smaller equation where we can express everything. Remember, Q and M are constant matrices, and C1 and C2 are functions of delta and tau, which are both like C2 and C1, which we need to identify. So the equation C1 minus trace beta 2, which is solvable for for given values of Q and C2. So once we find Q and C2, then we can identify C1 easily. Now the question is, how can you find C2? We have equation 10 where C2 is can be expressed as a function in terms of different constant matrices that we define in delta. Now, interestingly, we decompose this one in a different form, where dou by dou t of C2t can be expressed as C2. Remember, C2 is a function of delta and tau. M is a constant, where H is defined. H is called a Hessian matrix. It's kind of just like we can define only one term, the corner term, one-one-th term as a function of delta, and the remaining terms are zeros. Remaining terms in the sense, even in dimensional matrix case, it's only a single term exists there, and the remaining all of the terms in the H matrices are H matrix is 0. Now, based on that assumption, we came up with a partial differential operator for C2 with respect to the time tau, such a way that a C2 can be defined in terms of lambda matrix. So it's kind of like a connecting everything. So finally, we came up with a lambda matrix. It's the assumed matrix. Again, since we assume the matrix, we are considering the lambda matrix in terms of the exponential. That is evident from the equation 11, why we consider it as an exponential matrix. Then again, remember, the exponential matrix defined in 12 is not totally independent or constant. Exponential matrix defined in equation 12 comprised of the variable state space variable x and tau. So delta and tau. So based on that one, when we consider lambda 2 inverse and lambda 2 we can obtain C2. Again, we define a lemma. That lemma gives like the integral for C2 inverse. We need that one in order to obtain the C1. Because as I said before, C1 can be obtained from this equation C1t minus trace beta C2t. Once we get C2, then we can obtain C1 in terms of an integral equation. So basically, there are two integral equations we need to define. So the integral can be calculated based on the R code. Yeah, if time permits, I'll show you how the R code works as well. Now, again, going back to the assumption of exponential matrix, this is the part actually I really get in trouble. Even the problem remains unsolved now, because we know that like a stochastic differential equation can be solved, and we can express in terms of the exponential of a matrix. Now, what comes if the exponential of some kind of matrix, that matrix itself combined with the time variables, and we need to define just like how we can express this exponential matrix, and how we can calibrate back to the process or bring back to the process where the exponential matrix itself is varying with respect to the time. When I say exponential matrix varying with respect to the time, that means for each time frame when you get a matrix, that matrix need to optimize in order to calibrate the model, where the matrix itself is varying with respect to the time based on the input data. Now, it's a big, long structure that we came up with a derivation for the exponential of the stochastic matrix. So exponential of the dynamic matrix, and we need to come up with the lambda in the sense that we need to come up with a solution in order to get lambda 1 lambda 1 2 lambda 2 1 lambda 2 2, because our basic idea is that exponential, this need to express in terms of a matrix or in terms of a linear form. Then we can bring it back to a matrix form. Then we can connect lambda 1 1 lambda 1 2 lambda 2 1 and lambda 2 2. Then we can express everything together. Sorry, Kalyanam sir, you asked some question. You do have. Do you have any questions? Okay, so So as I said before, we started off with the lambda matrices, and then we can come back to the solution of the partial differential equation. I think I'm quickly moving to show you what the actual expression for it's a little bit just like 1 to 2 page derivative, but okay, so here again, coming back to the integral equation, as I said before, U is our Fourier transform. From this Fourier transform, we need to identify C1, C2. As I described before, we need to identify the actual solution. So based on this Fourier transform, what we do, we decompose them into two parts, the real part and the complex part. And the real part of the equation with certain condition will come under the risk neutral probability measure, and we define the probability survival probability corresponding to the model. So P is the survival probability, and then remember we made like lots of transformation. We have gone through the logarithm of Si plus di over di, then we transformed to e power yi over 2, then we did the Fourier transform, and now we are coming back to the probability equation, where the probability equation is just like an integral expression as given in 17. Now if you look at the equation 17, we can see that as C1t and trace of C2tx, since the trace is sitting there, it's a linear combination. And in the previous lemma, I explained C1t delta can be, again, a trace function. So the entire function, the exponent, the function on the exponential is totally a trace, which means it's a linear combination of lambda 1s and lambda 2. So the basic challenge here is that we need to identify lambda 1, lambda 2, lambda 1, 1, lambda 1, 2, lambda 2, 1, lambda 2, 2 for a bivariate case. It's the extension, we can extend that to the multivariate case as well. Now, the question is, basic challenge is like how can we decompose that stochastic or dynamic exponential matrix? Now, what we have done is just like we optimize the integral function in calculus function in our program, then use the optimal function in order to get the best optimal value in multidimensional space. This is just 2-dimensional. That is what I'm wondering, how can I show the actual real R code, because this is just like example is taken just for 2x2 case. The actual R code is based on multidimensional space for all the countries based on the entire data set. So again, in order to get the calibrate the model, we need to identify the mean and variance, which is another lengthy process. I don't think I do have enough time to go through. So these are the two big expression we came up for the mean and variance of the model. Then I'm not going through the proof again. Sorry, it's so this is the slide. I really wanted to bring it back. How we can connect the model that we build along with the existing model. Existing model is the model that we know is the CIR process. So the only way that we could check whether the derivation is accurate with respect to the CIR process, because the CIR process is well defined and we know what are the expressions for mean, what are the mean, derivation, variance, and like risk neutral probability, everything is available. So the only way to go back and check whether the derived model, the multivariate derived model can at least get some sense is that we can check corresponding univariate case, and this is what we defined. It perfectly matches with what we defined in CIR process when we bring the m-dimensional sovereign credit risk model back to the CIR process. I wanted to give a little bit more context because at this stage, even now, the calibration was successful. However, there were certain situations in which the optimization criteria stopped working on the R code. The reason is that optimization is on the convex region, on a multi-dimensional region. There are certain areas in which where the data considered entirely without categorizing to the recession time frame and non-recession time frame. The data is just like getting termination due to non-availability of the optimized value. So because of the same reason, the model is calibrated. However, we move forward with another algorithm which we need, which is called the Kalman filter algorithm. If time permits in a later time in future, maybe like I'll explain more on what we have done. Yeah, so this is the part, as I said before, this is really, I haven't seen in any of the literature so far. There was one article which shows like how exponential of the dynamic matrix can be defined in terms of a defined matrix. So this is the derivation. I'm not going into detail, but just wanted to show how it works. It's still an open problem. How can you find the derivative of the exponential of a stochastic matrix? So my intention here is to bring attention for at least one student to get involved, or any professors, those who are working in this area, to expand more so that we can all use those ideas to get the project complete. Now, I think I'm going to stop here. I do have like another 20-25 slides to explain what the Kalman filter algorithm is. So I think like I'm going to stop here for the question time. Thank you very much for your attention. Any questions, please?
Okay. You can ask questions, or you can also comment on the box, or otherwise give your suggestions or anything like this. Yeah,
Yeah,
sir.
Kalyana sir raised question.
See, I just want to express my happiness, Shanoja. Can you hear me?
Yeah, I can hear you well, sir.
I just want to express my happiness to see one of my children is coming up like this. I don't think that you have left anything from basic probability and statistics to high-end mathematics. Wonderful. Carry on.
Thank you very much.
All my blessings and best wishes. And we thank you back to the department and make us see that one of the children is doing it like this. Okay, all the best wishes. Yes. I may
Thank you
need
very much.
to understand what you have done. That much I can say. Yes.
Thank you very much.
1 year to see seriously what you have done, but I am able to see on a sketch what exactly you are doing here. Wonderful, wonderful.
Yeah. And I try my level best to incorporate the entire part in just like a tiny time frame, just like.
I could understand that. Yes, very much. I could understand that. Yes, yes.
Yeah, the entire topic is just like if I want to start off from the basic and go all the way to what we have done, I think it's just like at least 4 to 5 hours explanation I need to expand it. Yeah, it's not that easy because it took almost just like 3 to 5 months in order to get that solution.
So I said that's what I said. You have started from basic probability statistics.
Yes.
In mathematics. So wonderful.
Yes, sure.
Fine. It needs more time. Yes, sure. Yes.
Yeah.
Sati, thank you.
Thank you very much, sir. Really appreciate it.
Dr. Naik, it was a great lecture.
Thank you very
Try
much.
to cover a lot. And I think we need time to understand all this.
I
So,
know.
there was so much there. It was quite a heavy lecture.
Yeah, that's why I started off saying, okay, this is like a math heavy. It's
I
not
know.
just like yeah,
So you used stochastic calculus and
right.
those models, Cox model and all that. And the others who have not worked in this area, they need time to understand all this.
Yes,
Use
sure.
those Kalman filters and all that. You really need a very good background in stochastic calculus.
Correct. Yeah.
So, but you try to
Um,
cover a lot. Thank you
yes,
for that.
thank you very much.
So, if I need some help or I want to know something, I may be writing to you. I'll take your address from Professor Satish.
Oh
I'm
yeah, thank you very much.
I'm Kanchan Jain from Punjab University.
Nice to meet you, madam.
Thank you. Same here. Okay, bye.
Thank you very much.
Thank
Bye.
you.
I put my mail ID in the chat box if anybody wants to contact me. So I can send you the published paper and the technical writes up. I don't know whether I can share the technical writes up because it's still, the research is still undergoing. So I can share the one which we already published.
Yeah, I
Yeah,
like
if
to
you
have a
can.
copy of that.
Yeah, sure.
So,
Yeah. Again, the publication was basically on the data perspective. There was nothing much given in the actual context, in the sense the derivations and other stuffs are less written in that published article. Yeah, but I'm really looking forward to see whether I can progress well with the derivation in terms of like a stochastic exponential matrix, because that's a huge area we need to expand. Yeah, so that is what I'm looking forward to. Due to time sensitivity, I'm not getting involved now, just like staying slightly away from these heavy math.
yeah, very heavy mathematics.
Yeah,
Quite involved, actually.
yeah. Thank you very much, madam.
Okay.
Hello, Shanoja.
Hi,
I'm
Baiju.
Baiju. Yes,
Yeah, I got
we
you.
are classmates at the University of Kerala. And
Oh yeah, nice to meet you.
I'm so proud that you have presented a brilliant lecture on the respective area. And
Thank you.
congratulations that you have combined the probability theory, stochastic process, integral equations, and the stochastic differential equations, and so on and so forth. It is very nice, and it's amazing. And I thank Sadish Kumar sir also for assigning you as resource person in this workshop. I am also a part of the workshop. Anyway, congratulations. Thank you.
Thank you very much, Baiju.
Okay. Anyone else? Okay. Nowadays we have online platforms and there are a lot of facilities to communicate each other. So you can communicate, you can contact her via email or any other media. Okay.
Yeah, I think that's the only reason I'm able to be here, because if it's just like in person, then I may not be able to make it. So thank you very much for your invite and for having me. And again, thanks for the COVID. Because of the COVID reason, all of us, we are at home. That is how we make it in the Zoom meetings and Google Meets. So thank you very much for organizing. It's well organized, and so thankful to the department again for inviting me. And throughout my journey, I always remember, because our department is the starting point for my life journey in statistics. So, Kalyanram sir, thank you so much for your contribution during my studentship. And like I cannot just mention one person, but Yagin Sontama sir, Vrinda teacher, Lessa teacher, Muthu sir, everybody contributed in my life. Thank you very much for the department in having me.
Okay. Thank you. Shanoja. Maya, do you have any comments? Maya is. Maya T. Naik?
Yes, sir. Yes, sir.
Yeah. Do you want to add anything?
Yes, sir. I am seeing Kalyanram, sir. No more questions. A very informative session. And Kalyanram, sir.
Happy to hear your voice. Why don't you put the video on? At least, Maya,
Yes, sir. Yes, sir.
why don't you put the video on? I will just at least see your face.
Yes, sir. Video on, sir.
Yes.
Thank you.
Very nice. Yes. See, we all have only this property. Our children, whenever we see this, we become energetic. We will continue for another 2 or 3 years like this. So, very happy to see you all and taking part. Just to support Satish to a maximum extent. That's all we can do. He is doing wonderful.
Thank you, sir. Thank you, sir.
Right. All the best. All the best.
Thank you, sir.
In fact, I'm very much happy to have all of you with us, supporting our department.
No, definitely, I won't miss anything if I am informed in the correct time.
Yeah,
Definitely. Because our village is having some problem. So I make some arrangements for getting this connection now.
Okay. Thank you, sir. Thank you so much, sir.
Maya and Shanoja, etc., are something that I cannot even imagine. Baiju is not showing its face.
Thank you, sir. Thank you.
Bye, sir. Yeah. Everyone, in fact, very supporting. And your voice, as seeing you in this way itself, is again giving us a particular type of energy.
Okay.
Boosts our, isn't it? Yeah. Sir. Okay. Now let us conclude this session. Yes, sir. In fact, it is beyond words, Shanoja. You did a lot of things in a very nice way, in a very short span of time. In fact, lot of things put in a basket, as presented in a very nice way. And on behalf of the department, it is our duty to extend our gratitude. On behalf of the department and all participating in this meet, I extend our heartfelt gratitude to you, Shanoja, Dr. Shanoja. And our blessings are always with you. Best wishes. Best of luck. all the best wishes. And we need your service in future also. We will.
Oh, sure. Always welcome.
In January, we will conduct one more program utilizing Shanoja.
Sure.
Yeah. In fact, this itself we can form as one of the workshop program. Yeah, that way.
Okay.
Application oriented. What's the theory to application? In what way the students have to feel it? Okay.
Yeah. Sure. Yeah. Okay.
Motivate. studying.
Yeah, sure.
We are always giving importance to the theory as well as to the practical side. This is that amalgamate that thing procedure that requires more attention, and in fact we are proud of you, Dr. Shanoja.
Thank you.
Once
Thank you very
again,
much, sir.
Thank you all. Also, I would like to thank each one of you, professors, teachers, and other researchers, and my students, and participants from various parts of the globe. Dr. I think Kanjan Jain, you are also your presence also very valuable. Professor Piparagu is also with us. She will and several professors from outside also with us in this journey of via the distribution theory to the application side. Thank you once again. Thanking you, Dr. Shanoja, Dr. Kalyanam sir, other alumni as well as members as well as other professors. Once again, thanking you. Let us give a big clap to Dr. Shanoja for her nice speech, talk. And thank you all. Thank you so much.
Thank you.
Expecting your support in future also.
Sure, always. Thank you.
Yeah. Thank you. Thanks so much. Now let us. Oh, Professor Kachesh will also want to join, I think so. Hello, Professor. Professor Kachesh. Okay, let us join. Let us meet in tomorrow morning. Tomorrow morning session by Professor Kundu will start the session. Devashish Kundu of IIT Kanpur. Thereafter, Dr. Jagamar will handle the next session. And afternoon session is another junior faculty. In fact, even though she is presently she is the HOD of the Department of Data Science, she will handle. Okay, thank you all. Thank you so much.
Thank you. Thank you very much, sir.
Thank you.
Bye.
Thank you so much. Bye. Bye.
Bye.
Thank you, sir.
Thank you, Vijay.
ഒരു റിഫ്രഷർ കോഴ്സും കൂടെ ചെയ്യുന്നുണ്ട് സാർ, അതുകൊണ്ട് എനിക്ക് രാവിലെ ജോയിൻ ചെയ്യാൻ പറ്റത്തില്ല.
ഓ, അത് ശരി. ഓക്കെ ഓക്കെ.
അതാണ് ഞാൻ നേരത്തെയുള്ള സെഷൻ. പിന്നെ കുഴപ്പമില്ല, യൂട്യൂബ് വീഡിയോ ഉണ്ടല്ലോ, അത് വാച്ച് ചെയ്തോളാം.
ഓക്കെ ഓക്കെ ഓക്കെ. വെരി ഗുഡ്. മാക്സിമം നമ്മൾ ചെയ്യാൻ ശ്രമിക്കുന്നുണ്ട് അങ്ങനെയുള്ളത്.
താങ്ക് യു ഷനോജ. താങ്ക് ു സാർ.
Okay, thank you
very much.
Thanks.
Okay. Goodbye.
Okay.
Hi,
okay, bye.
Professor. Bye. Okay, Professor Kacheshvili from Georgia, Georgian Technical University. Hi.